that it? Sorry. I normally of course. Okay, sorry, carry on. Just
okay, so I'm
missed the first
actually writing things and doing things in four space-time dimensions, but this could be done in any number of space-time dimensions. So the Poincaré algebra, so where the MIs are the rotation generators, the B's are the boost generators, P is the PI is just a generator of spatial translations, E is the energy is the generator of time translations. As interesting contractions, and two of them have been particularly studied. One is a familiar Galilean algebra, which corresponds to letting the speed of light go to infinity, and with appropriate rescaling, this is what you get. So there is a simplification, as you can see. For instance, the boosts among themselves on R0 commute. And the other limit that I will consider here on this slide is the Carroll algebra, which is somehow the opposite limit, in which now it is the speed of light, c, that you let to 0. So, and after rescaling, so that the commutation relations remain finite, this is the algebra that you get. Again, the Carroll boost values, but you see that there are other simplifications. Particular E with B is 0. Okay, now, so these are from the mathematical point of view, particular contractions of the Poincaré algebra. Now, the Galilean algebra is rather familiar because it corresponds to the so-called non-relativistic limit, ordinary non-relativistic limit of Einstein's theory. And so small velocities with respect to the speed of light. And well, it has a central extension, which is actually probably the more relevant. But since I'm not going to talk about the Galilean algebra, let's not spend too much time on that. So it describes the non-relativistic limit of Einstein's. The Carroll algebra is relevant for the opposite limit when for what we call the ultra-relativistic limit, since we are letting the speed of light c goes to 0, and this would correspond, if you start from Einstein gravity, to so-called Carroll gravity. Now, I will discuss that in more detail later, but that was actually my historical motivation for considering the Carroll limit, the ultra-relativistic limit, because it turns out that it controls the dynamics of the gravitational field near a space-like singularity, as I will make a little bit more explicit at the end of my talk. And it turns out that this behavior is extremely rich and interesting. It has connection with infinite dimensional Bms algebra, hidden symmetries, and this is one of them. So I would like to discuss, as I said, Carrollian theories to begin with per se, and then I will review the connection with the KLB. And I will also discuss at the end infinite dimensional extensions of the Carroll algebra, which are relevant to the asymptotic structure of gravitational theories of Carrollian types, just like there are infinite dimensional extensions of the Poincaré algebra, which are relevant to discuss the asymptotic symmetries of Einstein gravity in the asymptotic Einstein context. Okay, so let me say a few words first about causality and compare Galilean causality with Carroll causality and with Poincaré causality. And I will do that on a very simple example, Klein-Gordon equation in Minkowski space, which is Poincaré invariant. And since we are going to let the speed of light go to infinity or to 0, I write it explicitly to see what happens. So in the non-relativistic limit, time derivatives are dominated by a spatial gradient, and if you let c goes to infinity, this term drops, and the equation reduces to Laplacian of phi is equal to 0, which implies instantaneous action at a distance. And in terms, geometrically, in terms of the light cones, you can view this limit as a limit in which the light cones completely open up. and becomes hyperplanes. The hyperplanes x0 is equal to constant, and then Galilean causality is very simple in such geometry, where you have absolute hyperplanes of simultaneity. Now, in the ultra-relativistic limit, it's the opposite. Time derivatives dominate spatial gradients, so you have velocities which are important, and the Klein-Gordon equation reduces then. Well, if of course you have to multiply it by c squared to begin with, and then you find that it is only it's just the opposite limit in which it is the time derivatives that survive. So it's second order ordinary differential equations with respect to time, xk being some sort of parameter. And in this opposite limit, what happens is that the light cones, instead of opening to hyperplanes, would collapse to lines. So the lines xk equal to constant, which are generated by the vector d by dt. And so causality, meaningful signal can only propagate without changing xk. So in particular, the field at time t will depend only on the field that is first derivative d by dt at time t equal to 0 at the same spatial point. This is a crucial dimension. So in that sense, ultra-relativistic is also ultra-local.
Sorry, this would be in the case of time-like thing. If we have a spacelike, that in this case we would tachyon in Carroll.
Yeah, then you could have you could have tachyon, but okay, that's right. Tachyon in that case, of course, can connect different spatial points, but somehow they would violate the naive Carroll causality.
Yeah.
And so, in general, for dynamical Carroll invariant field equations would reduce to ordinary differential equations with respect to time. There is a clear evolution parameter which is an absolute. Okay. Now, what I have been discussing here is one way to take the limit c goes to 0. There are many ways of doing that in a consistent way. I will only mention another one, probably many others. Well, there are many others, which is the so-called magnetic limit. And the reason for electric and magnetic will become apparent in a few slides. So there is also a different magnetic limit, which has also similar causality features that can be defined from the Klein-Gordon equation. And actually, that's true for any field theories, and that's also true in Galilean formulation and field theories. And that was pointed out in the case of Galilean electromagnetism 4D by Lebellec and Jean-Marc Lévy-Leblond, who constructed two different Galilean invariant formulations of electromagnetism, one electric, one magnetic. And that can also be done for Carrollian electromagnetism. That was done by that paper. And actually, that can be generalized to many other field theories, P-form, gravity, iris spins with arbitrary dimension. And that was done in that paper, and that also was considered in the cosmological context. That was okay, so let me spend some time now to tell you how to construct these Carroll invariant limits of P-form gauge theories before I go to gravity. And it turns out that these limits are most conveniently taken in the Hamiltonian formulation of the theory. So perhaps I'm saying this because I like the Hamiltonian formalism, so probably people who are used to Lagrangian formulation second order will find that it's very convenient in their language to also take the limit, but at least in the Hamiltonian formulation of the theory, it's rather straightforward to take the limit. Okay, now let me consider an arbitrary P-form gauge theory, and since I'm considering limit, I will first look at theories without interactions. So in the Hamiltonian formulation of a P-form gauge theory, so when I'm working in D space-time dimensions, I have a P-form, I have its conjugate momentum, which is the analog of the electric field. These are the spatial components, so latent indices are spatial indices. And then I have Lagrange multipliers because it's a system with a gauge invariant, they are constrained, and the constraints are accompanied by Lagrange multipliers, which are the temporal components of the p-form potential. And so the action takes this form, which is a familiar PQ dot term, but for the p-form. So I have the pi, momenta conjugate to the p-form times the p-form dot, so time derivative of the p-form. Then I will have a constraint term multiplied by the Lagrange multiplier. Okay, and this constraint is really the divergence of the conjugate momentum. So it's like Gauss's law, but for a p-form. And then I have the energy density. And the energy density has two terms. One term is of electric type. Recall that pi, the momentum conjugate to A, is the electric field. So I have electric field squared, E squared, with some factor, and I have subtract the factor of C. And then there is a magnetic energy density, B squared, but B here is just the spatial component of the curvature. And so in the free case, that's what we have. E squared plus B squared is the energy density. And then we have a constraint that generates the gauge invariances of the. Now the magnetic limit, maybe I should just. The magnetic, now we want to go to Carroll, go to the Carroll contraction, to the Carroll limit. And so the idea is that we just take C goes to 0 and nothing screams in terms of these variables if I take C goes to 0. And the effect of that is just to drop the electric energy density, and I'm only left with the magnetic energy density. That's why it's called the magnetic limit.
Excuse me, in the Klein-Gordon case, I think you did the opposite.
Yeah, I did the electric, which I will describe now.
But there you did a limit, you didn't restate. Could you go a moment back?
Well, but I was looking at the equations of motion.
Yes.
I have to rescale. Because if I take C goes to 0, I have a problem. So I have to multiply by C squared. Okay. And then this term. So I'm indeed describing first the magnetic limit because that's the one that comes naturally in this way of doing things. And so what you end up with is the only the magnetic energy density. Now the electric limit is obtained by rescaling the fields first, and you want to rescale the fields in such a way that the kinetic term survives because you want to have a dynamical theory. And so we multiply by CA, but then I divide by C the momenta, and the net effect, of course, let me go back to the expression here. So in other words, I'm absorbing ZC in C squared in this expression, but then I will have a C squared that comes from here because I have to rescale the Q in such a way that the commutation relations QP still 1. Okay, so if I do that, it's just the opposite term that will survive. It is this term that will survive. And then in that case, I get again exactly the same type of Lagrangian with a constraint because I have gauge invariance that is not affected by these limits. But the term that survives in the energy density is the electric part of the energy density. And for that reason, that's called the electric. And indeed, that's what I was doing in the Klein-Gordon case. And as I said, both limits are compatible with gauge. Now, if you look at the energy density, magnetic or electric, separately, it's very easy to see that they commute at 2 different points. The reason why they commute at different points, let me go again to the expression for the magnetic and for the electric energy density. Well, the electric energy density only depends depends on P. And P has a 0 bracket with itself Poisson bracket with itself. So it's clear that E at two different points will be 0 because pi at two different points have vanishing brackets. I will say commute using the language of quantum mechanics, but it's really vanishing Poisson bracket we are classical. Now F is solely built out of the spatial components A. So it depends only on the Q's. So this is a function of the Q, and if you take a function of the Q at two different points, two different functions of the Q's, they will again have vanishing Poisson brackets. So E with E at two different spatial points is 0, EM with EM at two different spatial points is 0, but the bracket between the two is not 0. But something else. And so for that reason, these relations are indeed rather straightforward. And it's actually because these relations are fulfilled that we can easily construct the corresponding Noether generators of the time displacement and the boost. They will be obtained by taking the energy density and integrating over space. For the boost, it's the energy density of first moment with xk integrating all over space. And it's clear that because E in the integrand at two different points commute, E with so this commutes with this, it's clear that E with B is equal to 0 and B with B is equal to 0. So this relation, which is characteristic of the Carroll algebra, is a consequence of that relation on the densities, which is fulfilled in the case of these forms. Now, the other relations can be easily verified to be a consequence of the fact that the energy density is a scalar under spatial translations and spatial rotations, so that this you are integrating a scalar. This automatically will imply that E commutes with pk and is Lorentz is rotation invariant, and pk will transform correctly because there is the xk. So indeed, the crucial relations for Carroll invariant field theory are these. Now, if you compare that with what happens in the Poincaré case, so if you compute the Poisson bracket of the commutator, the Poisson bracket of the energy density at two different spatial points, x and y, you don't get 0 because of the cross terms. And you find actually a relation which is universal and which contains the momentum density. And this was pointed out in the 1960s, previous century, by Schwinger and Dirac, who looked at the conditions for field theory to be relativistic invariant, and they arrived at this crucial condition under reasonable assumptions on the number of time derivatives, etc. But so what replaces this relation in the Carroll case is this relation.
So can I ask a question?
Yes.
Before you move on to the argument. So in the case of the scalar field, you show that the Carrollian limit gives you an autolocal field because you only get time derivative. Is that also true?
That's also true for the so you will get, of course, the constraints, which are so the constraints will have to be satisfied at each spatial slice, and so they act like the Gauss's law. So that will not involve time derivative, but somehow you need only to impose it at the as an initial condition, and then you can forget about it because it's automatically preserved. And then you can show that the other equations are also ordinary differential equations with respect to time, and that the initial conditions. So if you want to determine the field here, you only need to know the field at the same spatial point and perhaps the first derivatives, but nothing else. You don't need to know all the derivatives of the field spatial to know the field at a later finite time.
So, related to this, so in the case of a scalar field, where I see that the propagate the scalar field along the lines, here you're taking two limits. One of them, so normally
propagation of the electromagnetic field, but the electric and the magnetic components being propagated. We usually take the limit in such a way that you only propagate the electric field, but you only propagate the magnetic field along the line. Correct?
Yes, that in one case, actually what you call the electric field will be zero. I think in the magnetic case, if you look at, so pi will not anymore be the electric field, but the electric field, which is d0 ak minus dk a0, I remember correctly, is zero. But that's so but you would have a momentum, which is some independent variables, which is present. But that's essentially true. Yes.
Also, sorry to interrupt you. Are you going to say anything about quantum version?
No.
So can I ask a big question then?
Yes.
So this optimal locality is that compatible with the uncertainty principle? Because it sounds like the evolution of the field at a given point is completely independent of any other neighboring point. That sounds difficult to reconcile with the spread of the wave function.
Yeah, so I think that the concept of wave function has to be refined, etc. But you see, we have commutation relation, Poisson bracket relations between the field. In the quantum theory, they will go into commutators. So we will have non-trivial commutators, and in that sense, it's compatible with the uncertainty principle.
But so if I take the Carrollian field, if I look at a quantum theory about a single scale of field, and I take this limit, I get a quantum field theory with Carrollian symmetry, and then it's still true that the evolution at any point is independent of any one.
It would be in that case, in the case of electric limit of Klein-Gordon, it would be as if you had an infinite number of point particles.
Yeah.
At each point, you have a system which obeys the points don't talk to each other.
Yeah.
But it really becomes quantum mechanics.
Yeah. You can do that in quantum. You can go to quantum mechanics. Okay, so let's now go to gravity, which was actually my original motivation. And again, you can define two different limits of gravity, Einstein theory. And these limits can be taken in the Hamiltonian formulation. It's relatively straightforward if you go to the Hamiltonian formulation. And that goes as follows. So you start from the Hamiltonian formulation of Einstein gravity, which is the famous Dirac-ADM formulation. And so again, since we are Hamiltonian, we have two pieces in the Hamiltonian action. One, which is the PQ dot piece that tells me that P is conjugate to Q. So in this case, the Q's are the spatial components of the components of the spatial metric. And that's Q dot, and P is pi ij. So these are the pi ij. Now, geometrically, you can show that the pi ij are related to the extrinsic curvature of the equal time hypersurfaces. So this is for the kinetic term. And then you have constraints which are related to the fact that the theory is invariant on diffeomorphisms. It's again a gauge theory. And so you have diffeomorphisms that can be normal to the constant time hypersurfaces that are parameterized by the so-called lapse. And then you have the shift that parameterizes diffeomorphism tangential to the equal time hypersurfaces. Now, there might be surface terms that depend on the slices, whether they are closed or open with the boundary, and then that would depend on the boundary conditions. I will say a few words about boundary conditions and asymptotic symmetries at the end, but here I will not discuss that. So for that reason, I have not written the surface terms that might be needed to complement the action. Now, we get, by varying the lapse and the shift, the so-called Hamiltonian constraint, H, and Hi equal to 0, the momentum constraint. And they have the following expression. So this is just from Dirac and ADM. So H has a piece quadratic in the momenta, and the supermetric is a so-called Dewitt supermetric. And then there is some sort of potential term that depends only on the Q, which is this one. And then we have HI, which is the generator of spatial difference. I have done some rescaling and I have kept C explicit. Actually, there would be some factor in front, which I have absorbed in the labs. I will give the explicit, the complete expressions on the next slide. But the point I want to make now is that upon overall rescaling of the constraint, since they are equal to 0, one can do that. This is the way the Hamiltonian reads, and in particular, we see that there is a power of C. They don't have the same powers of C in here. And so I will take the limit C goes to 0, so that would be actually the way I wrote things and rescale the electric limit, because you see that if I take C goes to 0, now it's a potential term that drops and the kinetic energy density remains. So if I take C goes to 0, this goes away. And then you see that the expression for H, what remains of the constraint, fulfill that, again, this characteristic Carroll relation that if you take the commutator at two different points, sorry, the Poisson bracket we are classical, at 2 different points, you get 0. That was very obvious because you get the fields at the same point. So of course it depends on Q and pi. So you might say maybe it's not entirely obvious, but because the Poisson bracket is antisymmetric, we are really taking, and so when you are taking the field at the same point, by antisymmetry, it has to be equal to 0. You can check that. And then the other expressions are just telling me that HE, the Hamiltonian constraint, is a density under diffeomorphism. That's the way density transforms when you write that in terms of Poisson brackets. And that the diffeomorphism forms the diffeomorphism algebra, and that gives you this this relation. So this is actually just the algebra of the spatial diffeomorphism. But so what is important is that this relation, the dynamic HE H, the Hamiltonian constraint is a generator, is a non-trivial dynamical generator, and we see that at 2 different points it commutes. Which means that maybe I should not have said that. Yeah, which means that this is written, but I didn't say that the constraints in that limit remain first class. So we have, in a sense, a consistent limit of general relativity. Which preserves the number of gauge symmetries because we get the same number of constraints and they're all first class. The first class relationship is modified, but they remain first class in the sense that the bracket of 2 constraints is 0 modulo the constraints. Now, perhaps I should say a little bit more about the rescaling. So if you compare, so I rescaled and dropped the rescale, but if you compare with a standard formulation where N being the standard lapse and H being the standard Hamiltonian constraint, there is a rescaling, which I can do because it's only the product which appears in the action. And actually, the rescaling that I did was the following. So N is a standard lapse, and the rescale lapse is actually that. And H would be the standard Hamiltonian constraint, and rescaling gives me this. And so in the previous slides, I dropped rescaling. So I do the rescaling, and then I drop the notation rescaling, which is standard.
Sorry, this epsilon?
Okay, I will explain. What is epsilon? Epsilon, and actually it's important in the historical way this theory was discovered. Epsilon is what people, and actually Claudio Eitelborn, called the Hamiltonian signature of spacetime. Why is it so? If you look at the Hamiltonian formulas for Euclidean gravity with Euclidean signature, you will find that all the constraints are the same except the Hamiltonian constraints that differ from the Hamiltonian constraint of valid for Minkowskian signature by the sign in front of the spatial curvature. So epsilon is equal to -1 for Lorentz signature is equal to +1 for Euclidean signature, but the rest is the same. And so we see that taking the limit c goes to 0, taking the Carrollian limit, is the same as taking the limit of the gravitational coupling constant going to 0. So for that reason, that limit was called 1975 by Ayshan the strong coupling limit. But you can also see that this is somehow a signature intermediate between Euclidean signature and Minkowskian signature. And if you look, the only difference is the sign of the timeline directions. In Euclidean signature is +1, Minkowskian signature is -1. So what is in between is 0. So you would have a degenerate metric. You would have a 0 and then plus. Okay. So this limit, Carroll limit, is known for that reason under various names, but this is equivalent. Strong coupling limit, 0 Hamiltonian signature limit. And this was a theory that attracted some interest in the late 70s. And that's the way I got involved. I looked at that problem. Now, there is also a magnetic limit. Well, you can guess what it is. Let me go back. So you do some rescaling of the momenta and the metric in such a way that this remains invariant, no C, because you want to keep PQ dot. You want to keep the Hamiltonian formalism. You want to have a non-trivial symplectic structure. So if you rescale pi by some power of C, G has to be rescaled by the opposite power of C. But it's very easy to see that by doing this, you can transfer, by rescaling the pi's and the metric, transfer C, eliminate the C which is here, but then the price you would pay is that there will be some power of C occurring here. And then you take the limit, and you have also, well, you rescale also the Hamiltonian lapse, and you will have to rescale the shift also because you want to keep this gauge symmetry. But so it's clear that in that magnetic limit, the term that survives is this. So you drop, I didn't write anything. Sorry. And in that case, the magnetic Hamiltonian constraint, would only involve the spatial curvature, so the Qs. So it's clear that it obeys also this commutation relations. It's density under coordinate transformation, so you can also fulfill that. And then, of course, coordinate generators are unchanged and fulfill still this relation. So it's a consistent limit in which all the constraints remain first class. So these are interesting limits because it's very difficult to modify Einstein theory consistently. But here we see that there is this dramatic limit can be used to define theories that are still consistent in the sense of having the same number of invariances and degrees of freedom. Okay. Now I should, and that actually is related to a question. You find that in the magnetic limit, the metric will be independent of time. And that is the analog of the fact that in electromagnetism, that the true electric field, which somehow is a time derivative of the vector potential, is equal to 0. Okay, now you might say, I told you, well, we have a theory which is consistent, which has the same number of gauge invariances as the Einstein gravity with standard Minkowskian signature. Can we write manifestly covariant action for the electric limit of gravity, for the electric Carrollian limit of gravity? And the answer is yes, but the variables will not be the same variables. It will not be a Riemannian metric of Minkowskian signature. It's actually a degenerate metric of signature 0 plus plus plus. And this is actually suggested by the fact that we've seen that this limit was also the 0 Hamiltonian signature limit of general relativity. But then to keep the same number of degrees of freedom, you need to take into account that there is the determinant of G alpha beta will have to be equal to 0. And so something should replace the determinant. We have to introduce as an independent degree of freedom the volume element, which I call omega. Now, once you have a degenerate metric and a volume element, there will be preferred null directions, which will be the analog of the collapsed light cones, because this equation will have a non-trivial solution. But of course, the solution is determined up to rescaling. But if you can normalize this solution by requesting that this, which is a vector, which is a density of weight 2, and you can show, so this is a minor, sorry. So we compute the minor of G alpha beta, because G alpha beta is not invertible, and the minor, minor, just the determinant of the sub matrices will actually be proportional to an alpha and beta, because it will, when you contract with little g, you get 0, so it necessarily has this form. Then you normalize n using omega in this way. So it's the same. So in other words, this data, G alpha beta omega, is equivalent to giving you G alpha beta and beta with a specific normalization for them. And you can construct an action. I will not perhaps spend time on that. You can develop some geometry of this geometric associated with this geometric data. You have a metric is degenerate, so parallel transport you cannot in general construct. So curvature you cannot without extra ingredients. So curvature will not be naturally defined, but there are things that you can define. And in particular, you can define the analog of the extrinsic curvature, because you have a privileged time-like vector n. So you can take the Lie derivative of the metric along that vector. That will give you a tensor. The factor of -1/2 is taken to adjust to Riemannian conventions, but there is nothing deep in that. And you can show that this action is actually the covariant expression, second order expression of the Hamiltonian action for the electric limit that I wrote on previous slides. So there is a geometry that you can develop for Carrollian geometries.
But that was for the electric.
That was for real electric. The magnetic is more complicated, and we can discuss that later. Already the magnetic case is more complicated for electromagnetic. If you want to have a covariant action, we need more variables. We need auxiliary field to get some action. And also the action will be, you see here, we could go to a second order action. It's not clear that in the magnetic case, we can have a second order action. I think that the covariant action, or at least the ones we constructed for electromagnetism, are first order, but they are more variable. In a sense, we covariantize not only the vector potential, but also its conjugate moment, which becomes an independent covariant field. Okay, now the procedure of covariant, actually that's probably what I was going to say. Yeah. More work is required, but okay. So in flat space, for the action I wrote previously, you can apply this procedure, and you can write manifestly covariant action under the Carroll transformation. So if you look at the flat space action, so flat space would mean here a flat Carroll structure, so that the metric would just be reduced to delta AB, the space part, that would have 0 there. And the vector, you just, it's clearly a solution of G alpha beta and beta equal to 0, and it's like this. So that would be a flat Carroll structure. Then there is a privileged time derivative, which is a derivative along the privileged vector, which is an alpha. And you can show that in terms of these ingredients, if I give you, for instance, a scalar field or a p-form field, etc., I can write an action which is covariant, second order, and which reproduces the Hamiltonian electric action that I wrote. In the case of the magnetic limit, you can also do that, but it requires more work. And at least we could not take the limit directly from the second order action, Lorentzian action. We can do it from the first order formulation, but the second order formulation, we can do the electric limit, but the magnetic limit it's not so direct. Perhaps it exists, but we didn't do it. Okay, now why is this relevant even for Einstein gravity? You might say we are taking limits, but are these limits of any physical relevance? Well, there are many examples of physical relevance, but the one I will describe here, how much time do I have? 10 minutes?
Yeah.
Is
Let's describe this limit in terms of the theory. I want also take the limit for solutions.
yes, but of course the solutions will have to be, of course, since the
How should we think? I mean, say that I take the squash solution. I want to take the Carrollian limit and say that then that disappears.
that I didn't do the Schwarzschild because in a sense I was not so much interested in static solution, but much more in solutions in which time derivative dominates. Okay, and that's why I talk about BKL, but in principle, I think we could also look at static solutions of Carroll geometries. I'm not completely sure that they would be how physically relevant they will be. That I don't know. Okay. But in principle, yes, you have a theory, you can look at static solutions, and clearly they should be connected to the static solutions of Einstein.
So can I ask, it's a related question. I would like to know your opinion on this. So C is a dimensionful parameter. So really when you take, what you mean by C going to 0 infinity, say C going to infinity, for example, is that you take your original theory, you look at a particular dynamical regime, a situation.
Right. Exactly.
Where all particles, for example, move very slowly.
Yes.
Compared to speed of light.
Exactly.
Okay.
So we are really comparing velocities.
Exactly.
So
related to Lorenzo's question, then, if you look at the structure of black hole, which is a static solution, nothing is propagating or moving away. So the limit is clearer than that.
Yeah.
I think in that case you are probably setting G00 equal to 0,
Yes.
but that means that
Okay.
there is no force. I don't know. I mean, the gradient of G00 is equal to 0.
But didn't you say C going to 0 is equivalent to G going to?
Sorry?
You said C going to 0 is equivalent to G going to.
Yeah, again, because they are dimensionful
Yeah.
constants, it's a tricky, I mean, there are things hidden behind the assertion. You have to compare things which have the same dimensions. But the way I wrote things, I was implicit. So for instance, when I'm taking the ultra-relativistic limit, I'm assuming that the ratio of the time derivatives of the relevant phenomena with respect to the are much more, I mean, that the time derivatives are much more important than the gradient when compared with the speed of light. I mean,
Okay.
So I think that what happens in the Schwarzschild solution is that if you take the limit outside the horizon, then you're just not moving, there's no force to remain on radius.
Yes.
If you take it inside the black hole, then you're going to get.
Then you will end up with a BKL behavior.
But that's you see, I mean, because the way that it's working outside and inside is very different.
Yes. Okay, thank you. Okay, so I will describe a situation where okay, so it is known, and this is related to the work. I mean, this was really not related. It is it's a very, I think, deep result due to BKL that in the vicinity of a spacelike singularity. So we assume that there is a spacelike singularity, either like it can be an initial spacelike singularity like a Big Bang type, or it can be a spacelike singularity inside black holes. But they show that if you they considered pure gravity in 4D in the initial work, but that can be extended to 2D forms, as in extended supergravity models. Then they show that the dynamics of the field can be described in simple qualitative terms. And the reason being that the time derivative dominates. And so the description of the dynamics at each spatial point can be expressed in terms of the solution where you only keep the time derivatives. If they dominate, you look first at a situation where they are the only things. And the solution where you have only time derivatives is known, is a Kastner solution. It's generalized because at each point you have an independent Kastner solution, each spatial point. And also when you have extra fields, you have to take to generalize Kastner, but that can be done. For which, in the case of Kastner, the spatial gradients are dropped, so as if they were exactly zero. These are homogeneous solutions. And this is this is the work of BKL. It requires some investment, and this is what is now known as a BKL limit. And you can show that this behavior dynamic can be mapped on the motion of a billiard ball in some portion of hyperbolic space. Okay, but as I said, the fact that time derivatives dominate and that you can, and I will, there is a qualification that I will be more precise on the next slide, but that you can neglect spatial gradients is exactly the same thing that you obtain by taking the electric Carroll limit. Because the electric Carroll limit, you are dropping the terms with the spatial gradient and then the spatial curvature. And so the Carrollian limit is in fact then the relevant limit in the vicinity of a space-like singularity. Now, what I said why waveforms are included in the okay. It turns out that if you look at pure gravity, which was the original case considered by BKL, spatial gradients are dominated most of the time, but not always. And they may be they are important episodically, if I can say. And they are responsible for this oscillatory behavior from one Kastner solution to another. And they can be handled by representing them as effective terms in the Lagrangian, depending on the field. So from that point of view, the Carrollian limit in the case of pure gravity is not an approximation valid all the way to the singularity, but only for a limited amount of time. And then you have to take another Carrollian solution and then another Carrollian solution. The Carrollian solution is Kastner, or the analog of Kastner. However, when you include P forms, you can show that you can literally drop spatial gradients, all of them. And so the theory is literally described by the Carrollian limit. So in a sense, when P forms are included, the situation is better. I can give more information on that if you are familiar with the description, but this might be too technical. But so let me summarize by saying that in the case of gravity coupled to P forms, which is a very interesting situation, because that's what you obtain from supergravity and extended model of supergravity. Or if you take an P form can be a one form. So if you take Einstein-Maxwell, for instance, that would also, then in that case, the Carrollian limit is a good limit as you take a good approximation as you take the limit of going to the singularity, as you go to the singularity.
Is this result which should have scalar fields as well as P form?
When you have scalar fields, it's also true. And actually, if you have Einstein plus scalar, it's true, and then you don't have this, and a Kastner solution will be valid all the way to the singularity. Yeah, so it's in a sense pure Einstein gravity, which, as you see, what happens. So in the case of scalar, there is no oscillation. I mean, you have a Kastner forever. In the other case, when you have P forms, there is a transition from one Kastner to the other. You can have a change in the Kastner solution, but this is induced by the P forms. And a homogeneous P form can already do it. So if you just keep the electric energy density of the P form, that will have the effect of generating the BKL behavior.
I mean, you said that if you include a scalar field, then it is very different from the pure gravity case.
Okay. Now,
That's strange, right? Because you do relate it to Carrollian reduction.
Yes, but if you do Carrollian, there is also a vector field. And you can show that both the vector field and the scalar field will introduce this infinite dimensional oscillation.
But it's consistent to take just to exclude the. You can have a consistent reduction.
It's a consistent reduction, but the nature of the solution. So it will be like setting equal to 0 the vector field.
Yes.
Of course, this is consistent, but this is a set of measure 0 solutions. Now, I should say that all these BKL analysis is always for generic solution. And so which means that if you have such a solution slightly perturb it, you will generate a small electric field will be enough to destabilize and to have the oscillation. And actually, I should say, depending on the model, sometimes for gravity, you always take the electric limit to describe the BKL. For the P form, sometimes it's a magnetic part which is dominant, and most often it's the electric part which is dominant. But no matter which one you have to keep, it works. Okay, so in particular, for 11-dimensional supergravity, it is, in that case, not only the electric part of gravity that you have to keep, but also the electric part of the 3 form. So 11-dimensional supergravity, you have gravity plus the 3 form. And the BKL limit would be obtained by taking the electric Carrollian limit for both gravity and the 3 form. So you would keep the term quadratic in the momenta for gravity, the term quadratic in the momenta for the 3 form. But they are symmetric to saturated displacement. And this would be the standard kinetic term. Now, there are, of course, also Chern-Simons term, but you can show that in the limit they can be dropped. And so the limit of 11-dimensional supergravity is described as you go to a singularity by the Carrollian limit, which is simpler. And actually, one can look at the dynamics. And as I said, one can map it on the billiard motion of the portion of hyperbolic space. And that portion of hyperbolic space for 11-dimensional supergravity turns out to be the fundamental Weil chamber of the infinite dimensional Gas-Moody algebra E10. So, the E family of groups is well known to be connected to 11-dimensional supergravity. So it was half a surprise to find that by going to the BKL limit for 11-dimensional supergravity, we would get the Weil chamber of E10 to describe the motion near a singularity. And that is really in the Carroll limit, which applies. So that was work done with Thibault Lamour and Van Nicolas. Now, maybe briefly, I went over time. Or
I go for another minute or two. We've already asked you many questions.
yeah, there were questions.
Yes, we've so.
Let me switch to another, I think, extension, which is the asymptotic structure of Carrollian gravity. So what are the asymptotic symmetric groups? And to describe the asymptotic symmetric groups, I first would like to point out that there are many ideas of the Carroll algebra, but 2 of them at least are relevant for the asymptotic structure. So I've rewritten again the Carroll algebra here. So B with B0, B with B0, and you see that, and also let me read terminology. I will call PI spatial translations and spatial rotations. The kinematical transformations, they are defined at equal times. But then I will call the boost and the energy, time translations and boost, dynamical transformations because they involve time evolution. Now, it's clear that the kinematical transformation form a algebra, so translation in space, rotation in space, which is just the algebra of Euclidean displacements. I mean, 4-dimensional space-time, so 3-dimensional space. ISO 3. In homogeneous. Now, the dynamical transformation, this is E and B, and you see that they form an ideal. Why? Because the bracket of anything with E will be either something involving B or E, and the bracket of anything with B involves either E or B. So you see, then with B is B, but if I take the bracket or is 0. So it's clear that B and E form an ideal. And the quotient of the Carroll algebra by that ideal is just, of course, ISO3, the kinematical generators. But then there is another ideal, which is the energy itself, because you see that the commutator, the brackets involving the energy, well, are 0, so it's an ideal. So it's even an abelian ideal, which I call E, and the quotient of the Carroll algebra by that ideal will be isomorphic to the semi-direct product of ISO3, the kinematical generators, by the boost, which I don't take the quotient, which form a three-dimensional abelian algebra. Of course, when E is equal to 0, you see that E with B is equal to 0. So they transform into vector representation of ISO3, just like we see from here. Okay. Now it turns out that each of these finite dimensional algebras have infinite dimensional extensions, which are relevant for the asymptotic symmetries. So if I take the full Carroll group and I look at the homogeneous Carroll transformations, rotations, and boosts, I can extend it by super translations. And the super translations will just be functions on the sphere, and they will transform in an infinite dimensional representation of the homogeneous Carroll algebra and commute among themselves. So that would be the contraction of the familiar BMS algebra, and then, as it has been shown by Alfredo Perez, in the magnetic limit, this would be the asymptotic symmetry algebra. Now, it turns out that you can decompose super translations into even and odd. And you can show that if you take all the even super translations, so we have seen that the energy for Carroll is an ideal. It turns out that all the even super translations, which includes the energy, but it's an infinite dimensional subalgebra, actually is an ideal. And so if you take the quotient of the Carroll BMS, so this one, by the even super translations, you get something consistent. And this is what we call D3 BMS algebra, because D3 refers to the fact that D3, we take the quotient by the energy. Here we take the quotient by the energy, and in this bigger algebra also by the even super translations. But then you can even be more radical and take the quotient by the boost also, and that would be the extension BMS algebra, ISO3 BMS algebra. It turns out that this is that. Oops. It turns out that one can devise, and this was done by Alfredo, boundary conditions in which the asymptotic symmetry algebra is this one. But in recent work, which will be soon on the web, we have also other boundary conditions which realize this other infinite dimensional BMS type algebra. So I think that the asymptotic structure is quite interesting, and I think it's interesting also to see how it's connected with how we take the limit at the level of infinity, directly at infinity. Okay, so let me conclude now, since I have been a bit over time. So the standard non-relativistic limit in which C goes to infinity has been well known for a long time. There exist powerful methods to develop the theory powers of 1 over C and control the successive development. There are extremely refined methods to do that. But the opposite limit is also useful. One case where it's relevant is the BKL analysis of the vicinity of a spacelike singularity. But there are many other gravity-related contexts where it appears. For instance, when studying precisely the BMS group, we do get a structure which is a Carroll structure at infinity. There are also examples in cosmology which have been recently studied by the paper by De Boer and collaborator. So this limit is also interesting. It has been much less studied. No, it is, I think, there is a missing less. It is not been very much studied. But the C equal to 0 limit itself, has been studied. You can actually quantize the system. It's more easy because it's ultra-local. So effectively, it's like finite dimensional mechanics. But what has been much less studied is the systematic powers in expansion in powers of C. There have been interesting works along these lines, but the degree of refinement of this expansion is far less from the degree of refinement of the standard relativistic group. And with this, I would like to say.
Does anyone have any more questions in the room they're not asked along the way? Yes.
There's an interesting connection among Carroll and Galilei that essentially is mapping the energy with the special momenta. Therefore, I think it will be curious to see if the Carroll limit that you have obtained by contraction in the past with Carlos Valle and the student of here, Diego del Mastro, we saw the non-relativistic contraction. Therefore, my intuition is that the two of them are connected. That's okay. Something that probably one can check rather quickly. And the other thing has to do with your later comment about corrections. And the point is that at the level of the algebra, it is known what are these corrections that are sort of Kazmudi sort of infinite dimensional algebra. And these corrections are such that the corrections, if you enlarge the dimension of your space, the correction has a symmetry. And in that sense, the corrections to Carroll will be no longer ultra-local, but it will start having a derivative. And this, in a way or another, should be related to a truncation of this infinite dimensional algebra that I am saying.
Yeah, perhaps one could use the symmetry, the duality between Galilean limits and Carrollian limits to derive information here from these methods there. Yes.
Probably. Yeah.
That could be very useful.
Okay, I don't know very much at the level of the field theory. I know at the level of the algebra, and also at the level of the realization of particles, particle and corrections map one each other, and it's work to be finished with such a change.
So anyone remotely, I'll just check if anyone remotely has a question before we go. Yeah, I think Axel, do you have a question?
Yes, that's right. I do. In fact,
We take this and then.
I have.
But Axel first, maybe?
Yeah, should we take the remote one and then you guys continue talking? Yeah.
So, go ahead.
Okay.
Axel.
So I have a question about the BKL limit. I mean, you said there are some cases where you have to take the electric and some cases where you have to take the magnetic.
Yes.
If I remember correctly, there are also cases, and probably pure type 1 supergravity in 10 dimensions is one of these cases, where the billiard is formed by both the magnetic and the electric part of the same field. So some of that, what kind of Carrollian limit would that be?
I think that's a good point, and especially there are. You see, I don't think that the electric and the magnetic limits. Well, I know, and you know that probably better than I, that the electric and magnetic limits exhaust all Carrollian limits, and in particular, in four-dimensional electromagnetism, where we have duality between the electric and magnetic, I mean, E and B have the same dimension, I know at the level of the Hamiltonian of another limit which fulfills the criterion of Carroll invariance, and that it has both E and B.
Mhm.
So you cannot drop, I mean, so you take the Carroll limit and you get both E and B. And I would suspect that in the special cases where you have self-dual, or where you can have self-dual forms, you would have to take this more tricky limit for the P forms. I don't know if this is the case you have in mind.
Well, I think the case where I have in mind isn't self-dual, but still it's something where somehow you keep both electric and magnetic.
Because the walls have the same. Usually,
yeah.
Either the electric walls are dominant or the magnetic walls are dominant, and you keep the ones that are dominant.
Mm.
But if both are the same, it could be that the walls coincide, in which case there's some form of duality. Then I think the limit might be more interesting in a sense. It does not fall into that simple category.
Oh,
I'm
yeah.
sure that there are other limits.
Okay.
Which actually, I think that there is, for instance, in 4 dimensions, a Carroll limit of electromagnetism, which is duality invariant.
Ah, that's interesting.
I can even write the Hamiltonian, but I cannot write it in covariant form.
Thank you.
Yes. I just understand, so when you say that the idea of the algebra is connected to the asymptotic symmetries, and then we use this to calculate the Bms for the.
Well, I mean, this was very short. I mean, it turns out that the asymptotic symmetries can be extensions of one of these quotient algebra. Okay, and so it's really okay. So really, the way we realize that is to first compute the asymptotic symmetries and then try to connect them with the Carroll group, and then we realize that they were infinite dimensional extensions, either of the Carroll group or of the Carroll group with. You have to take the quotient by an ideal, and we just saw which ideals in each case was to be considered.
Is that so you're saying here that the systematic expansion powers of C that has been much less studied, and I imagine that this is because this is probably a more singular limit, in the sense that maybe around this point the expansion is not convergent, can have non-perturbative effects. And that's not unusual when you one end convergent until the end.
Yeah, perhaps it's not convergent, but perhaps also. But I think that even to write systematically the first term and then ask whether it's convergent or whether there is a way to reproduce, that has not been done. I think actually they are developing such an approach in the context of cosmology, because I've seen a paper very recently by Oberst, is part of the report, and I think they are trying to develop systematically such an approximation. I don't think that they address questions such as convergence or which.
Well, I mean, so you just can't see that you expect and that effects come from some quantities that you can.
That's right.
One other thing. Wouldn't be surprised if there's such a thing. This limit is more similar, or is less. Well,
yeah, because in a sense you have also to open the light code.
Yes. Yes.
In fact,
In a sense, it's more easier to slightly to go this way than to open the light.
This is a more degenerate.
Yes.
but that it happened that if you do the corrections, the light can open in these papers that will appear soon.
Yeah.
And that has been computed.
Yeah, maybe I can comment on it. It looks like more degenerate, but to make a connection also with duality. You see, in our case, Carroll, you have a degenerate metric Now, in the case of Galileo, the Einstein-Cartan formulation, you would have a contravariant symmetric tensor, which is degenerate. And actually, the hyperplanes are precisely because you are in the dual, so they associate. So in that sense, there is a great similarity, and I don't know whether we can say that one is more degenerate than the other. But there is some sort of duality between Carroll and Galilei at many levels.
In 1 + 1 dimensions, they would be essentially equivalent.
Exactly. Exactly. In 1 + 1. And then it's really replacing space by time.
In fact, in 1 + 1 dimensions, this duality thing that we did with Andrea Bartucci and Roberto Castabuoni, it becomes an isomorph. And also another comment in this direction, maybe, is the fact that view that was introduced by Guy Gibbons and collaborators. If you introduce some Carrollian time that they call S as a new constant, a velocity x0, essentially the expansion, it is done 1 over this capital C, this new velocity we introduced, and formally you send this C to infinity, and many of the things, it goes in parallel. Still, you are sending, in the ordinary case, C going to infinity, the velocity of light, and in this case of Carroll, we are sending to 0. I send it to infinity, this capital C. Therefore, okay, I don't know. Okay, I think I don't know.
In what they call the Bachmann space, which has even one more coordinate.
No, not on that. No. Simply that the time, the Carrollian time, they define in this form, and the Carrollian energy is also defined according to the evolution of S. And if you do that sort of thing, things are much closer, at least in many respects, of the limits to the standard case. But or the physics of gravitation.
All right, I think that sounds like now questions in here. It doesn't look like anyone remotely asking questions, so should we thank our speaker again?
Thank you. So